Hello, folks. Welcome to Rational Science. Today we seem to have God as as part of the audience. Okay, that's good. I better behave today then. Anyways, we're going to be dealing with dark energy today, a little later on. But let's start with the situation in the world. And we have a situation there in Ukraine. The Russians have incorporated two of the provinces of Ukraine into the Russian Empire. Okay, so let's all pull out the champagne bottles and celebrate. Okay, and like I said in the past, I'm saying this war has nothing to do with Ukraine. Okay, this war is against Germany. Germany lost the First World War, lost the Second World War. Germany is going to lose this war as well. This is a loss for Germany. And here you have Schultz. He's the chancellor of Germany, and others like the prime minister, the president, right? And he says that Germany has taken steps to halt the certification of Nord Stream 2, which is a gas pipeline that comes from Russia all the way to Germany. And it was about to be certified, but now they're going to postpone it. And it's important to know that the head of that project is a fellow known as Schrodinger, who was chancellor of Germany in the past and good friend of Schultz. And so I'm sure they're not very happy with the fact that the United States is imposing this on them. It's like a lose-lose situation for Germany. And you can see there it says pressure from the United States. And a pipeline bringing natural gas from Russia to Germany increases Europe's reliance on Russian energy supplies. That's what the United States fears, that Germany might fall too much or too far into the Russian sphere. It's already fallen into the Chinese sphere because China is its number one partner as far as business is concerned. And so you can see that the United States is a little worried about that. And there are situations where for example, the United States wants to punish either Russia or China. And I'll just give an example. Let's say the United States says to China, we're not going to sell any more cars to you. And then Germany steps in and says, oh, we can sell you some cars. We'll send you some Mercedes Benz or whatever. And so that's what the United States wants to stop. The United States wants Germany on board with the other 50 stars. Okay. And not only Germany, but France, essentially France and Germany. I think those are going to be the big losers this time around. And yeah, because in the case of Russia, it's already made some pacts with China. So I think Russia has somewhat a solution to its problems, its economic problems. Not completely, this is going to hurt them, but they have at least resolved some of the issues before they went into the Ukraine. But France and Germany, I don't know, they're going to have to switch their economics, adjust it so that they fall more in line with the United States empire. And so it's going to be interesting what's going to happen in the next few years if we make it that far. And all I can say is, on the other hand, you got to look at the United States. And I've said it before, I'm going to say it again. The worst thing that can happen to the world right now is for the U.S. economy, for the American economy to collapse. If the United States economy collapses, we are all dead. Okay? And so right now we got to do everything possible in our power to prop up the U.S. economy. I don't care what your political leanings are. That's what we got to do. Okay? That's all I'm saying. Okay, and here you see a version of that, not mine. This is from the New York Times. Leonhardt, he writes the following. He says, political freedom has declined every year since 2006. Democracies are in decline, and that's all over the world. Okay, and that says that U.S. and Europe are struggling to lift living standards. Okay, so this is an important point there, and I guess one of the reasons for that is primarily Europe is already completely developed. There's not much more you can develop here in Europe in the next few years. Yeah, you can expand some services. You can maybe expand a little bit your manufacturing, but it's all done. It's like if you want to put a new business, what are you going to put? A car company and compete against the big corporations that exist around the planet already distributing cars? It's going to be very tough for you to beat those big companies. Aside from the fact that they might buy you off from the start and just neutralize you if you have some good product. And there it says major political parties behaving in anti-democratic ways. And this fellow apparently has a beef against the Republican Party. He put that as an example. But his last statement there, that's the one that's really gets through to you. It says the American-led order is in deep crisis. Okay, now, of course, you may not agree with what this fellow is saying. Uh, but all I can tell you is you don't want the U.S. economy to fall apart. And one of the problems you've got there is that empires do need to expand. If they don't expand, like the Roman Empire, once it reached the borders of the barbarians, they got stopped. And what was interesting, they hired a lot of these German, barbarian generals, and some of them eventually ended up attacking Rome. So you figure out how this is going to play out. And that's in one side. There's another issue that was popular these last couple of weeks, in fact, and it's this lady. Her name is Gu. She's a skier for China, but she was born in the United States, raised and educated in the United States, but she competed for China. And Nikki Haley, who was ambassador to the UN, she was really upset at that, and like many other people as well. And they're saying that she weighed in on American-born skier and Beijing game star Eileen Gu. Haley said Gu needs to pick a side between the U.S. and China. Every athlete needs to know when they put their flag on, you're standing for freedom or you're standing for human rights abuses. So she didn't like the fact that Gu, who's from California, speaks perfect English, went there and got medals for the other side. How can you do this? Okay. And all I can give you is my take on this, and that's that, all these sports games, they should remove nations from it completely. We got this from the city states in Greece, where each city state was a country. It was all the pals, all the buddies in our hometown, and that was the nation, the city state. And so when they got together, everybody fought for the city state. But that was, 2,000 years ago. Today, you would think that we've evolved from that. And it turns out we still have nations today, and people fight for the nation. Now that's okay in a military way. You want to fight for your country, go ahead and fight for your country. But in sports, should we have nations in sports? When Argentina and Brazil play soccer, it's a big deal. And they start the game by playing the national anthems. And they do this all over the world when two nations play. And the question is, are these uh, 22 players on the field, are they doing it for the country, or should they be doing it for sports, for the hell of playing, of having fun and having a good time? And the same for the Olympics. In the case of the Super Bowl or World Series, they only play one national anthem. I never understood why. But the issue is, should we have nationality into sports? And I think that's where the problem begins. If we didn't have nationality into sports, there wouldn't be any sabotage or anything like that. people would just go to China or to Russia or to the United States and just have a good time, and everybody just watches the best athletes on the planet. It would be great if we could get nationality out of the whole picture. No flags, just an individual medal. If you want to have a medal contest for medal or for prizes or whatever, that's fine. But it's when you put the flag into sports, I think that's when trouble starts. So I think all flags should be removed from sports, and people should just have a good time and play for the fun of it. And then if we're not worried about the country, then maybe we get that off our backs and we can play better in the field. But if people are thinking, oh, what is my country going to think of me? And it turns out, you listen to your anthem, you put your hand in the heart, and then when your team loses, they go and lynch you. your own countrymen go lynch. Okay, so I don't know. Anyways, let's move on to another issue, and it's this. We have the Moonies and the Loonies and the Flat Earthers. Okay, what are the Flat Earthers? Well, people who say that we've never went to space, because if we happened to go into space, we could have very easily taken a picture or filmed, the Earth from afar, and we would know if it's round, if it's flat. We would know if it's spinning. We would know a lot of stuff, right? Just by looking at the movie. And a human doesn't have to go up there. We could do it with, just a satellite or whatever. And then we have the Moonies. The Moonies say we never went to the moon. Okay? And you have all kinds of ranges there. Some people say we haven't even gone into space. Others say we haven't even gone to the moon. And obviously, if that's the case, we'll never go to Mars, because some people believe a human cannot escape the Earth and live, partly because of radiation, partly because of vacuum. And then you have the Loonies, and we're going to deal with those today again, one more time. For those of you who have something better to do, well, don't do it. Just stick around, and you might learn something. And so you have these Loonies, and they believe that the moon spins. And no, we're going to argue that the moon does not spin. Okay, so let's start with this fellow. We're going to start with some of the comments, questions people made, and they're all related to these Loonies that believe that the moon spins. Okay, here's the first one. It says, the moon spins, and said nothing else. Okay, it'd be nice if you say a little more than justify that the moon spins. That's a lot harder. And so to say and make a statement that the moon spins, you said nothing. Okay, nothing that concerns science, at least. Okay, another fellow says, the moon has an axis that rotates with it, so the moon doesn't spin. Earth's axis doesn't rotate with the planet, so it spins. And he was essentially saying repeating what I said, and he said it correctly, so I hope he understood it, and I hope everybody else understands it. And there's an illustration of that. The moon spins together with its axis, and I put a three-dimensional axis there so you understand the concept. That's what we're looking at here. We're not interested in belief. We don't care if you believe in this or not. It's irrelevant. Right now, we just want you to understand the concept. The concept is that if the moon spins, what we're saying is that the axis that runs through it does not spin. But if it spins, like in that case, together with the moon, then the moon is not spinning, because any point on the surface is not changing its distance with respect to that three-dimensional axis. On the other hand, in the case of the Earth, it's as if we had a solid, fixed, standalone, unmovable axis, three-dimensional axis again, and the surface moves and changes its distance with respect to each point on that axis. Okay, so that's the concept, that's the definition we're going to go with. Okay, if you don't like it, all you got to do is bring your definition, and hopefully you address the issues that will be talked about today. Okay, so here, fellow said it correctly. I hope you understood more or less what I'm saying. Okay, another fellow says, he says, It's quite confusing. It's quite a confusing analogy. Yeah, he's quite confused, no doubt about it. It says, is it not the case that the moon has ice caps top and bottom? Okay, that would mean that it spins or not spins in relation to the sun as well as the earth. Well, I'm not sure what the fact that it's got ice caps has to do with the sun or the earth. You know, he hasn't made his point. Okay, and isn't the moon just tidally locked with the earth in the first instance? Well, let's find out. What is this tidally locked? We have no idea what this is. Okay, let's find out. It says, tidal locking between a pair of co-orbiting astronomical bodies occurs when one of the objects reaches a state where there is no longer any net change in its rotation rate over the course of a complete orbit. In other words, you have a rotating body. Let's assume at some point the moon's spun around, and over the millions of years, slowly it slowed down until it finally gave a single face to the Earth, and it no longer spun. Okay, and so now it's tidally locked because it doesn't spin. Yeah, that's the issue. But the interesting part also related to that is high tides and low tides are caused by the moon. Okay, and the moon's gravitational pull generates something called what? The tidal force. Newton discovered or theorized that the moon affects the tides on Earth. Okay, and so well, it goes on and on, but this is the issue. Here's the Earth and here's the moon. Okay, and the question there is, what causes the tides? If the moon is 380,000 kilometers away, how does the moon affect the tides? How does the Earth compel the moon to have this? What is it? The fact that it's tidally locked. In other words, how does the moon affect the Earth physically, and how does the Earth affect the moon physically? If you don't put something in between there, then you're doing your theory with ghosts and with angels. Okay, that's what it is. You're doing black magic. Hopefully, if you're going to talk about tidally locked or tidally anything, the moon affecting the tides on Earth, hopefully you can tell us the mechanism, and you can tell us how one object affects the other through 380,000 kilometers of distance. Okay, and you can't use concepts. That's even worse. You might as well use ghosts and angels. Okay, so again, anyone who uses these notions of tidally locked and says that the moon affects the tides on Earth and that kind of thing, no problem. I think they do. The question is, what is the mechanism? If you can't tell me the mechanism, don't just say things that you read about or copied and pasted from the Wikipedia or whatever and say, oh, see, it says tidally locked here. Yeah, explain why. Explain the cause, the mechanism. Then you can talk about tidally locked. Okay? Otherwise, don't mention it. Okay? Don't say that mass did it or energy did it or a field or a force. Time. Okay, and then says a better analogy might be the rotor in an electric motor, as it has a shaft to rotate about. And I discourage the use of the word rotate, okay, because rotate is ambiguous. You can rotate around a planet, meaning you orbit it, and you can rotate around your axis, meaning you spun or you're spinning. And so the question is, whether we should use the word rotate, which is so ambiguous. And I'm going to encourage everyone to use the word spin or orbit, because those are very clear cut in the minds of most people out there. Orbit is what you do around something else. Spin is what you do around your own axis. Okay, and so I'm going to stick to spin and orbit and stay away from the word rotate, which is what is confusing this fellow up here. Okay, it's the confusion comes from using synonyms which have never been defined. In fact, none of these words have ever been defined scientifically. And that's what we're going to talk about in a minute here. Okay, it says, you go on, another fellow, you go on about defining axis as being a 2D, 3D object made up of two spatially abutting, non-coinciding planes, which you call edges, when all this has nothing to do with why you believe Moon actually rotates with its axis, whereas Earth does not. Well, the first issue we have to look at is this word believe. We have nothing to do with belief. This is not about belief. This is explaining a mechanism based on a definition because we're trying to justify the definition. And what we're doing here is, just putting a definition and arguing the fact that spin has to do with a fixed axis. That's how we're defining it, and that's the definition we're using to explain this phenomenon known as spin. Okay, and so I'm giving you something objective. If you don't like it, you got to come back with an objective definition and argument. Not say that we have a belief. There is no such thing as belief in science. Okay, so this word belief should exit your mouth and your brain. You should come into science talking about objective explanations, objective mechanism, objective causes. That's what this is all about. Okay, and yeah, I'm gonna go in a minute again of why we use this 2D or 3D axis. Okay, and I'm gonna get that in there in a second. Okay, but here you see essentially why we need that axis there. Okay, and why we need anything other than a one-dimensional axis. But the problem here is this word rotate, which is equal to spin. It's also equal to orbit, and also equal to every other word like spiral and so on. So rotate is a word that we do not want to use. Let's use spin and let's use orbit. What is spin? Spin is circular motion of an object's surface with respect to what? Its fixed axis. The axis has to be fixed. Okay, and in the case of orbit, it's the circular elliptical motion of a body around another. Okay, so these are different. So if you look at the guy in the first, the guy who's walking around in circles there, is he spinning? Well, no, he's orbiting. He's not spinning. Okay, why? Because he is not spinning with respect to his own axis. Okay, and so the question is his axis standing still or not? Is it moving with him? And right now we have no indication that it is standing still, and we have no indication that it is moving. And I'll tell you why in a minute. Okay. On the other hand, the fellow on the right looks like he's spinning, but again, we won't know, the guy in the center, because we don't know if his axis is standing still or not. Okay, and again, that's gonna be the argument, whether the axis is standing still, whether it's moving, whether it's fixed or rotating together with the object. Okay, and people say, "Oh, what are you talking about, Bill?" Okay, let's find out. Here we have one more fellow. He pointed out something related to this, and he said, "Points and lines are axiomatically defined by their what? Parameterization." Here lies the rub, okay? So when you look at parameterization, process of finding parametric equations of a curve, a surface, or more generally a manifold or a variety defined by an implicit equation. What is a parameter? A constant or a variable, a numerical or other measurable factor. In other words, he's saying that points and lines are defined by equations, numbers, variables. No, not in science. Okay, maybe in mathematics. Maybe that's how they define things there, which is not a definition at all. So no, it's not defined through parameters or anything related to equations or numbers or variables. That's exactly the problem. You end up with situations like in quantum mechanics where they define spin and they say, well, it's minus half spin or one spin or plus half spin. What do you mean minus half spin? What the hell is that? I thought spin was spin was spin, and it turns out that spin is a number, one of these quantum numbers. And so no, we don't define spin with numbers. Not if you're later on going to insinuate that that means that the thing is spinning like a top. One thing has nothing to do with the other. The fact that a top spins has nothing to do with the notion of spin. For example, for an electron, when they talk about electron spin, they're not talking about it spinning, the notion of spin that we normally have, right? We're talking about orientation. When you measure at that point in time, it's got a given orientation. That's what they say. And the orientation is either up or down. So what kind of spin is up? What kind of spin is down? What kind of spin is minus half or plus half? And again, this is the problem. We do not use numbers to define spin. The other thing is that you should be aware of is that spin is a physical phenomenon. It belongs exclusively to physics. In mathematics, there's no such thing as spin. They have no use for the word spin in mathematics, pure mathematics, okay? Now, the problem is that the mathematicians, they started venturing into physics. And so they created this religion known as mathematical physics. And that's when they put numbers together with things, concepts together with objects. And they blended them together and created a big mess. And we've had this big mess at least since the days of the Greeks, and it hasn't stopped till today. So, you talk about a singularity, like a black hole singularity, and you say, okay, I know what a singularity is. It's a little dot. No, singularity is a number. Okay, it's a number. That's what a singularity is. It's got to do with equations. It's got nothing to do with a dot, for example. Okay, again, that point, the word point, means two things. It means the location and it means the dot, both. That's what mathematical physics has done throughout the ages. Okay, they blended things with concepts, and that's where they ran into trouble. Okay, and that's why they got space-time, four-dimensional space-time, unimaginable. They don't care. It's four-dimensional space-time, and then you ask them, why does the Earth fly out of the solar system? Well, they said there's a depression in time. We have warp time. What the hell is that? Okay, why? Because they've turned time into a physical object. They blended the physics, the fishnet, together with a concept called time. They put them together and they said space-time. You got it, right? Yeah. That's how it's done. Okay, but it turns out this guy says lines are axiomatically defined. Are they? When I look it up, this is what I see, okay? You correct me if I'm wrong. Points and lines says axiomatically defined. And here you look it up, it says point and lines are undefined terms. Everywhere, I mean, these are from the Google. I just Googled points and lines, and everywhere you see undefined terms, point and line, and plane also. So all these are undefined terms, admittedly by everyone out there, okay? So everybody essentially says that points, lines, and planes are undefined. So I don't know what this fellow says that they're axiomatically defined, okay? But then, after saying that these points, lines, and planes are undefined, they go ahead and they attempt to define them. Here it is. These are what you find for point. Point is in geometry is a location. It has no size. No kidding. How can it have size if it's a location? There's no such object called location. Objects can only have size, and these people are talking about the size of a location. And then they say a line extends infinitely. Well, then if a line extends infinitely, it's not an object. It's not a thing, because there's no object that is infinite. All objects are finite. In fact, it's a synonym of the word object to say that it's finite, meaning that a line is a concept. There's no physical standalone object called line, and yet they always draw a little line, right? A little elongated rectangle to represent the line. And they say the line is one-dimensional, but yet what they draw is always two-dimensional. So the elongated rectangle. And wherever you look, you see this, location and size, location and size. Okay, all of them talk about location and size. And so that's what a point is. And the line, what is a line? Well, a line really is one of two things. It's either a row of apples or an apple that's moving down the street, okay, an itinerary of an apple. And both those notions are the line. and the mathematicians use whichever one they need at any given point in time, depending on the context. Okay, so we have a problem. We have a problem because we don't know what a line is, and it turns out the line is one-dimensional, and it's made of zero-dimensional points, which makes no sense whatsoever. So what are these people talking about? Well, it turns out the point is not even a point. It's in other words, it's not the dot that you're staring at. It's the location the dot supposedly represents. And a line is, again, one of two things. It's either an itinerary or it's a row of apples. And so they use these concepts mixed with objects, and they put these pictorial representations of these concepts, and people confuse the pictorial representation with what it represents, the concept it represents. That's where the problem is. And again, it's because math and phys, they can never be reconciled. Mathematics has nothing at all to do with physics. And that's where the problem is, okay? And people have problems understanding that. That's one of the first things you got to grasp. Okay, and another fellow says, no, I'm sorry. This is an outline of what I'm saying that mathematical physics has done over the years. They equated concepts with objects. That's what it is. And they say that an object exists is also equal to an object. Why? Because objects are defined as that which you can touch or see, and exists is that which you can touch or see. And that's why these words are synonyms. And that is not true. Not at all, not in science. And what is a dot? It's location. They call it a point, both of them. The dot and the location are called point. What is a line and itinerary? It's also a row of apples. Okay, so a line is both. Surface, they equate it with plane. Number, they think it's a thing. No, a number is not a thing. Number is a verb. Number is action. Number is moving your arm up and down and counting apples or whatever you're counting. Number lines equal to coordinate, number line equal to dimension, number line equal to vector. All these are synonyms according to the mathematicians, okay? And that's not true. The coordinate, dimension, and vector belong to physics exclusively. Number lines belong exclusively to mathematics. Never the twain shall meet. And then they say that space is 3D. So they take a solid and they say 3D space. Yeah, sure. No, space doesn't have any dimensions whatsoever, and you should not confuse the black stuff in the night sky, that dark stuff, which they say is filled with dark matter and dark energy. You should not mix that with the object. It's the question of if you put your rubber ducky inside the bathtub, it displaces water. Well, the volume that it occupies you can say is the space, whereas the rubber ducky is what is 3D. The space is not 3D, okay? Because there is no such thing as 3D space without the object. Okay, and then we have the things of mathematical physics. They've turned everything into a thing, and these are all concepts. The force has turned into a particle. They talk about particles of different kinds of forces, the four forces of quantum mechanics. But what is a particle? It's a function. But then they have wave is a thing, energy is a thing, field is a thing, time is a thing, singularity, information, everything is a thing. And they start moving these so-called things around. And that's where they run into trouble. Okay? So, yeah, this is the issue. The issue is that what mathematical physics has done is reify concepts. And they use them back and forth. When they want to talk about the concept, they talk about the concept, and then they represent it with an object and move that object around. People think they're moving, they say, we're going to move love now, and what they're moving is a heart. Okay, we're going to move the point, and the point is the location. You don't move a location. Hopefully not. I mean, maybe after 10 beers. Okay, so here's the rationale behind the axis of mathematical physics. And this is where you really have to pay attention now, okay? Why is it irrational? Well, because they start out with a point, it's zero-dimensional, okay? Why? Because it's really a location, meaning it's non-dimensional, not zero-dimensional, non-dimensional. No concept has dimensions, okay? So they start off on the wrong foot. But then they're going to construct their line with all these 0D points. They're going to say it's a 1D line. So we have a 1D line constructed of 0D points, which are not 0D. They're locations, meaning they're non-dimensional. So far, we have nothing in front of us. But they put a row of apples, or they put a solid line across there, a solid elongated rectangle, and they say that's a line. And no, that's a two-dimensional thing, hopefully made of two-dimensional dots, right? That's what we have objectively in front of us. And they say, well, make believe. Make believe that it's one-dimensional. Make believe it's zero-dimensional. Well, I can't make believe because I cannot imagine zero dimensions, okay? No object is zero-dimensional. So when you talk about zero-dimensional object, you're talking about nonsense, okay? And that's the problem. We've had this all the way since Euclid, okay? And they're still using these notions today. That's why you end up with a singularity, which is zero-dimensional. And you say, okay, you got nothing so far. And they say, oh, yeah, but that one moves stars around on the other side of, gazillions of miles away, so-called black hole. And you say, hold it, this singularity moves a star far away, moves it around itself? How did it do that? And forget about how they did it. Please show me a zero-dimensional singularity. Show me that it's an object to begin with. Because if you have a concept, how does a concept move a star? That's the question. Okay, and here we have again, the 1D line can be a row of apples on an itinerary of one apple. Okay, and the axis is alleged to be a line, in other words, 1D line. That's how they define the axis since time immemorial. Okay, but then the question is the mathematical axis a row of apples or an itinerary of an apple? Which one is the axis? Well, I can assure you that they're going to be using the row of apples and not the itinerary of an apple. They're not going to, for every point, they're not going to say, okay, let the point in the center move upwards and create the axis, okay? And it's just an itinerary. And now the object that's going around, whether it's spinning or orbiting, that's going to establish its reference to an itinerary. No, they want you to believe at that point that the axis is really the row of apples, a solid line. Okay, they're going to have this solid line, but this solid line, keep in mind, is one-dimensional, made of zero-dimensional points. So there you have it. That's what it looks like. The one-dimensional mathematical axis, that's what it looks like nothing. So far, they have nothing in front of them. Why? Because they're not going to be interested in spin or orbit. They're going to be interested in distance traveled, actually, not even distance, separation. They're interested in distance travel. And what they care about there is numbers and units. 5 meters, 10 feet. That's what they look at. They look at distance traveled by the tip of your measuring tape. Okay, so many meters, so many feet, so many yards, so many miles, that's what they look at. And so that's what they're going to be looking at, and they're going to use as a reference a one-dimensional line axis, okay? And that's what they're going to base their spin, with respect to that, okay? And yeah, mathematics is abstract, which is exactly the opposite of physics, which is physical. And what MathViz has done, it's irrational because it's trying to merge the abstract with the physical. That's the issue. Okay. Okay, so what's the problem with the mathematical axis? Well, it's one-dimensional, and give me a second here. Okay, I'm back to normal. Okay, so what's the problem with the axis? Well, here's the problem with the axis. Okay, here's the mathematical axis. It's either a row of apples or the trip of one apple. And both of them are regarded as lines in mathematical physics. Okay, so it doesn't matter if you have a row of apples or the trajectory of one apple. Mathematical physics consider these two notions, which are irreconcilable. They consider them as lines. and that's what they call it. And that's going to be your axis, one of these two. And they're going to insinuate the axis is really the one on the left, the one, the row of apples, because you can understand if you have a stick there that you can move around the stick. You can't move around an itinerary because it's like what's left after the apple's gone. Well, there's nothing there. The row of apples you can imagine because you got a stick there, but an itinerary you don't have anything left. Okay, so they're going to insinuate that the one-dimensional axis of mathematics is the one on the left, the row of apples. Okay? So what's the issue here? Well, I put the other day a two-dimensional stick because there is no such thing as a one-dimensional stick. And the problem there, the big problem there, and the reason these people never discovered this in the last 10,000 years, none of them, okay, is that we don't know if a one-dimensional stick spins, rotates, spirals, or whatever, orbits. Can a one-dimensional inexistent stick do anything? And even assuming, God is the only guy who can see the one-dimensional stick, fine. So we'll take it up with heaven, okay? So God is looking at this one-dimensional stick. Can he tell? I mean, he's all knowing, right? Omniscient. Can he tell whether a one-dimensional stick, right, one-dimensional line is rotating, made of zero-dimensional points, by the way? Is it rotating or not? Well, you can't tell because it's one-dimensional. It's not fat, it's not thick, it has no width. So there's nothing to gauge whether the one-dimensional axis is spinning itself. That's why the mathematicians never discovered it. When they take a distance, they take the distance whether the stick is standing still or spinning. It doesn't matter to them because they're going to look at distance traveled from this one-dimensional concept. And again, spin is a three-dimensional notion that belongs to physics. Okay, we're talking about a phenomenon that objects can do. And these people are saying, okay, we're going to drive a stake, one-dimensional stake, through the object. That's going to be our axis, and we're going to gauge whether something is spinning with respect to that axis. Well, again, the issue of whether the axis itself is spinning or not makes a big difference, and there you see why. Here you have the two-dimensional axis. I painted, color-coded each side red and blue just to make a point, and that's that you have these two edges. And the distance of the ball changes with respect to those edges depending on where it is around that circle. Okay, so it's straightforward. And I do it with a 2D, I can do it with a 3D as well, like I did last week, okay? And so the issue here is that, if that stick, that two-dimensional axis rotates, it's very different than if it doesn't rotate because the distance from each point on that stick to the ball changes. You can't do that with a one-dimensional line, one-dimensional axis, because it has no width, no thickness, no nothing really. There's nothing there, and so you can't gauge whether whether it's spinning or not, the axis itself. And that's why they never discovered that. They only look at distance and whether the 1D stick, when the axis spins or not, the distance is the same. Whereas with 2D and 3D, it's not the same. Okay? And again, spin belongs to the 3D world, not to the world of abstract mathematics. Okay? So this is where we have a problem with all this. And that's why they never figured out the definition of spin. For them, it's just a question of distance, and not a question of whether the axis itself spins, because they cannot even imagine an axis that is spinning or even standing still. You cannot imagine an axis, a 1D axis. Okay, so it's because they introduced this notion, this concept called the 1D line, made of 0D points, by the way. Rub that in whenever I can. It's because they introduced this notion and then translated that into physics. And they say, oh, the Earth spins. Why? Well, because the surface is moving around an axis. And the axis is 1D, made of 0D points. Rub it in one more time, So No, there is no such monster as an axis, a 1D axis. If you're going to talk about spin, you got to use 2D if you want, fine, just to make your point, just to make your argument, just so that people understand your argument. And better yet, 3D. You know, you put a cylinder in there. Then you say, well, does the cylinder stay put or does it also twirl with the object, like in the case of the moon? And so here's the conclusion to all that. Here you can see why the moon doesn't spin. And you see the moon compared against the moon, left to right at the top. And if the axis moves around together with the moon, with the surface of the moon, then it's not spinning. Okay, so I don't care if it takes 27 days to go around the Earth, and it, as people say, it rotates once around its axis. No, it don't, because if I put a stick in through the moon, a 3D stick, if I drive a stake right through the moon, the stick is gonna move together with the surface. Then it's not changing its distance, the surface to the stick at any point in the stick, and so it's not rotating. It's not spinning, which is the correct word. In the other scenario on the upper right there, that's wrong, and that's not what the moon does. The moon does not. The surface of the moon doesn't. Any point on the surface of the moon doesn't change its location with respect to that fixed axis, to any point on the axis. Okay, and then you see the moon versus the Earth. The Earth does spin because the axis of the Earth is fixed, and the surface moves around a fixed stick. And so the distance of any point on the surface of the Earth changes with respect to that axis, to any point on the axis. And in the case of the moon, it don't. That's how simple it is. Okay? Do you agree? I don't care if you do or not. Science never cares whether you agree and whether you believe. Okay? In science, we try to understand the concept, and if you have a better concept, then you get in the ring with shield and sword and defend your concept. That's the way it works. Okay? Very simple. Okay, and here we have another fellow. He said, is the thermosphere 5,000 degrees or not? This is what NASA claims is the reason why we can't get past low Earth orbit. I guess one of these moonies who believes we never went to the moon because we would go through the thermosphere and fry. Astronaut would, you know, maybe the rocket makes it through, but not the astronaut, because he would be fried at 5,000 degrees. Okay, and please explain the physics of this layer of the atmosphere. Okay, let's explain that very quickly, very simply. Okay, this is what this fellow missed. Okay, the thermosphere, okay, it extends up to about 1,000 kilometers above the Earth. The temperature is about 2,500 degrees C, yeah, maybe around 4,500 Fahrenheit. But there's not enough gas molecules to transfer the heat to you. Imagine if I take a match. Can you be burned by a match? I mean, can you put your finger there on top of that flame and stay there, you know, for 2 hours, assuming the match stayed lit long enough? No, it would burn your finger. But see, I can throw that match at the astronaut, and it's not going to burn him. And that's the issue there. You don't have enough matter. You don't have enough atoms. You don't have enough molecules at 1,000 kilometers above the Earth. Even though it's hot, there's very few molecules to really burn you. Okay, so an astronaut could just be outside his capsule at 1,000 kilometers above the Earth, and he would not fry, because even though the temperature of each molecule there could be as high as 2,500 degrees, there's not enough material there to burn him. Okay? Aside from the fact that at that point they usually go inside their rockets, okay? Inside their capsules. Okay, so hopefully you understood that. Let me get these out of here. And then finally another fellow says, I like this one. Another Mooney says, we never went to the moon, right? Why? What's his argument? I think that's what he's proposing. I think that's what he's saying. We didn't go to the moon. Why? Well, he's saying that, went through the other side. Give me a second here. OBS has that thing where you can overshoot and it takes your thing out to the other side. He says Mount Everest is littered with hundreds of bodies. The moon doesn't have one dead body. So I guess he's looking for proof. If we find a dead body on the moon, then it means we did go to the moon. But if we don't find a dead body, then we didn't go to the moon. You need to look deeper into the Moonies' claim. What can I say? People look for proof, evidence that we went to the moon. And no, we don't do proof or evidence in science, first of all, okay? And you can make an assumption. Say, let us assume we went to the moon and explain the theory with that. And you can explain many types of theories with that. One could be gravity and whatever. For example, you could say, why did the hammer and the feather, when they dropped it on the moon, why did they fall at the same time? And so you make the assumption, let's assume we went to the moon, we threw these two things, and this is what we observed, and now you try to explain gravity, so you could use that for anything. But this belief that people have, or unbelief that we went or didn't go to the moon, it really plays no important part in science itself, in physics. Okay? So do not harp on it. But I can tell you that I doubt very much that a program that has lasted at least since the 1960s, that's 60 years now, and thousands of people working year after year after year, decade after decade, and that all that is a hoax. This is not like JFK's assassination. This is not like 9/11 that happened in 1 hour or whatever. This is something that's gone on for years. You can go to Cape Canaveral, you can go to Houston or Jet Propulsion Labs, and you can go there and find out what they're doing if they let you in. And they send these rockets, and you don't even have to be inside there. Like I said, you can take your telescope, and you can take your camera, your super duper camera, and watch how that rocket goes out, right? And you can film all of it, and you can see that it goes out into space. In fact, the Skylab is still rolling around the Earth, and if you have a good telescope, you can see it. So what is that thing up there? I don't know. Maybe angels? Okay, here we go with this dark energy, this evil dark energy. What is this dark energy that these people talk about? Well, the other day we talked about dark matter, okay? And we found out that the mathematicians, because we're talking about the mathematical physicists, what these people do is they say dark matter is this, this, and this, and that. Okay? And then the next sentence they say, but we don't know what dark matter is. What? Did I hear right? Dark matter is a particle, it's heavy, it's dark, but we don't know what it is. Well, you just told me what it is. Well, what do you mean you don't know what it is? You just told me. And that's the situation, okay? So we have this situation here, okay, where they say, well, look, it's particles, it's ultra heavy, it's dark. Actually, it's not dark, as I showed the other day, or argued the other day, right? Invisible, translucent, or transparent, but not dark. You can see right through it. And you can see the stars and galaxies right through the dark matter halo of any galaxy. So this dark word is wrong, okay? It's misleading because people say, okay, they're bowling, like the 8 bowling ball, or the 8 ball in billiards, or even the bowling ball. The bowling ball is black, dark, right? And is that what this dark matter is? Just a bowling ball? And the answer is no, because if it were black, if it were dark, we would not be able to see through it. And right now we can see through it. Therefore, the word dark is wrong. It should be transparent, translucent, invisible, maybe, any of those words. And so now they're trying to find this stuff. The astronomers are pointing their telescopes. They're trying to see it in the night sky, around the galaxies, maybe between the galaxies, right? And the particle mathematicians, the ones who run the accelerators, well, they're smashing protons and who knows what else to see if they can produce this stuff in the lab. Okay, so that's the situation with dark matter. And we had the other day one fellow, his name is Victor Toth, and he talked about this. You know, if you can watch the previous lecture, you'll find that, you know, what he had to say essentially about dark matter. And again, a lot of these people are trying to find new equations for this. And here's dark matter. There you see it. Okay, you see the galaxy, and you see the dark matter around it. That's what they're saying that dark matter is. Bunch of particles. You got to think of each one of those particles as very, very heavy. Okay, extremely heavy, because they have to produce the mass, the gravitation necessary to prevent, first, stars from leaving the galaxy, and second, it's got to hold the galaxy together, and then it's the stars on the outside have to travel faster than the ones on the inside. And the only way you're going to do that, according to mathematics, is, you know, by putting these heavy particles on the outskirts of the galaxy. And of course, they can't see them, but they say they're there. They've been proven, and so deal with it. Deal with it. You don't like it? Take math. Okay, and this dark matter is also between galaxies. Okay, we find it, that's the theory. Okay, more than a theory, they say they've proven it, now they're looking for it. Okay, but they're saying this dark matter is also between galaxies. And why? Because they believe that galaxies, especially that are relatively close together, influence one another, and they don't see anything in that region, and so they say, well, there's got to be some dark matter, some very heavy stuff to produce what they observe through the scopes. Okay, so that's more or less where all these people stand. Again, dark matter has been proven beyond a shadow of a doubt. You don't like it? Take math. Okay? That's the answer. Okay, the problem here is that you don't find this dark matter between the moon and the Earth. Okay, so here you have the moon and the Earth. You don't find it in between these two objects, because if you were to find it there in between the Earth and the moon, since it weighs so much, right? One little grain of sand of one of these dark matter bits weighs tons, and it would affect the gravity between the Earth and the moon, or any object. For those of you who believe we went to the moon, right? Any object that dares go to the moon, it would change everything, because the gravity would change. So what they're saying is that if we sprinkle dark matter between the Earth and the moon, both Newton and equation and Einstein's equation, they would both fail. Okay, so you can't sprinkle it here. It's not there. They're not looking for it between the Earth and the moon. They're looking for this stuff outside of the galaxy. And what they've never justified is, why is this dark matter outside of a galaxy and between galaxies, but not within a galaxy? Why isn't it here between the Earth and the moon, where we could verify it, right? So yeah, one would think that these people are chasing ghosts. You know, this is what it amounts to. I mean, what else do you call it? The curtain moves, and you say it's a spirit of my grandmother. And you say, hold it, what do you mean the spirit of your grandmother? Maybe it was the air that moved it. But the guy's convinced that it's the spirit of his grandmother, you know? Okay. And this is more or less what dark matter is. You know, it's the spirit of your grandmother out there moving the galaxies around. And why can't we see it? Well, you can't see a spirit, see? It's a soul. It's a concept. Abstraction. Okay, so here we have it. This is dark matter conundrum, again, for you to understand what dark matter really is, and that is that the little yellow thing there at the end of the red line, that's a little star, and you can see that the one above is closer to the center of the galaxy, and the one on the bottom is farther away. And that's going to be the radius there, the r on the denominator, okay? And so if you raise the little r, if the radius increases, the little v, which is the velocity of the star, should come down. The problem is that when they put their scopes out there in space, in the galaxies, they see the opposite. They see that the stars on the outside are going faster than the ones on the inside. So the farther the radius, the faster it goes. And they say, how can that be if the equation suggests the opposite? If you raise the distance from the center of the galaxy to the star, if that increases, velocity should go down. And so the way they fixed it, they say, oh, we got to fix for it. See, again, they're not doing physics. What they do is just play around with the equations. And they created this variable known as dark matter. And it's mass. That's all it is. And so they put it in the equation and say, okay, that's the only way we can explain it. We've proven it, the existence of dark matter, because it's the only way we can justify that equation. We have to put dark matter in the numerator, quite a bit of it, in fact, all these kilograms that they put in there, right? And yeah, you can't see a kilogram, so I guess that's why dark matter is invisible or translucent or dark or whatever. Yeah, kilograms, it's very hard to see a kilogram. You know, you can see the bag of potatoes, but not the kilograms, okay? But so they put all these kilograms in the equation. Thanks to that, they are able to mimic with equation, they are able to describe with equation what they observe, what the astronomers observe. And so they said, we've proven it, because what else could it be? Angels, you know? But then they ask everybody to go out and look for it. And they asked astronomers, go look for it. And they asked the particle mathematicians, go look for it. Okay, everybody's looking for this stuff. What's the problem with this? Well, again, if you can see there the size of those galaxies, and you see the halo around the galaxies, well, it turns out we can see right through them. Okay, that's what happens. You can see right through the halo of the galaxy. So here's the halo, the way they imagine it. So they say, okay, there's dark matter there. Okay, well, if it were dark, it means it would be opaque, and you would not be able to see, you know, the stars in the background, but you do. You see it right through the edges of the galaxy. So again, the question is whether you can talk about dark matter, or, you know, why didn't they call it what they should have called it? Transparent matter or translucent matter. Then it would be great. But to say that it's you know, dark just confuses things even further, because everybody thinks that these folks are looking for little pebbles, maybe the size of bowling balls for all we know, that weigh as much as a whole Earth. That's what they're looking for. Very heavy stuff, particles. You can call a bowling ball a particle, but at the universal level, it is a particle, right? And they say all these bowling balls are around the edge of a galaxy, but they're translucent. Yeah. Okay, so what's this got to do with dark energy? Well, if you create the sin, you have to create the, you know, the absolution. You have to absolve the person, okay? You have to pardon this person. So you have to create this two-world thing, okay? This duality. And what they did, you know, if you have dark matter, which is something that pulls inwards, it's a gravitational effect that this mass produces, then you have to explain why the universe is expanding, which is what happened when 1929 you had Hubble. He kind of proved to all the mathematicians out there that the universe was expanding. And later on in, 1998, I think it was, 1998, 99, they went in there and they said, oh, we know what it is. It's this dark energy that's pushing space-time, you know, it's expanding space-time outwards. So you have on the one hand dark matter tugging in everything, all matter trying to get together, one with the other, right? All the galaxies trying to get together with each other. But then this dark energy is so overwhelming, it's pushing everything apart. And it's the struggle between good and evil, okay? The good, you can say, is the gravity trying to pull everything together. The evil is trying to separate everyone, make everybody an enemy of everybody else. Kind of like what's happening in the Ukraine. Okay, so where do we start? Well, we have this poor fellow, his name is Feynman, and he was a Nobel Prize winner. And he said, it is important to realize that in physics today, we have no knowledge of what energy is. So they're going to be looking for dark energy, but they don't know what it is. And the question is whether this dark energy thingy is kind of like the dark matter. Like, you know, what is dark matter? Well, it's a particle, it's heavy, it's dark, but we don't know what it is. Okay, and what is energy? Well, it's this dark matter. It's this dark energy. It's particles. It's heavy and it's dark, but we don't know what it is. Is that the answer going to be here? And you have some people who question whether that is the case. But here you have Mr. Toth, whom we presented last time around. And he said the missing matter is called dark matter, but the remaining stuff with negative pressure, again, you know, if you have gravity is positive pressure in this case, right? Dark energy is the opposite. It's negative pressure. It's pressure outwards in the universe, right? And you can see dark energy is 73% of all the stuff that fills the universe. Dark matter forms 23%. And all the visible stuff that you see out there is only 4%. Total of 4%. That's the calculation. Okay, so he says at the bottom, he says, yet at the same time, we have not the faintest clue as to what these dark thingies really are. And again, I don't understand because they've already defined what it is. They're saying it's little balls that weigh a lot, particles, right, that weigh a lot, and they're dark. So we know what it is. It's particles that weigh a lot that are dark. That's what it is. We're done. It's like, you know, what is a dog? Well, a dog has two ears, two eyes, a tail, you know, a body. But I don't know what a dog is. I thought you just described the dog. I don't know what a dog is. Okay, so here we have the Big Bang. So this is where we start. We had the Big Bang, and everything is pushing outwards from the moment of the Big Bang. Okay, you can see it here. Here's the original explosion. Okay, that's the Big Bang. Frame number 2, because they never start frame number 1, and everything is pushing outwards and creates this glass that's tilted. All the beer came out of it. Okay, so this is where it starts, and what they're saying is what's pushing all this matter outwards is dark energy. Inwards is what dark matter tries to do, but dark energy is more powerful, and it's just pushing the entire universe, this universe outwards. Okay, and when they do that, they run into this balloon analogy, and here it is. Okay, and what they do is they have this thing, which is the explosion of space-time that you just saw, and it starts from nothing, from a little point, okay, which you'll see here, okay, and it just expands. And what's expanding all that is known as dark energy. What's trying to pull all these galaxies together, the yellow dots there, is dark matter. But whatever dark energy is, it's winning the battle, and it's pushing the whole universe outwards. Okay, and this is what they talk about. The question is, what's the white stuff? What is it pushing out against? And that's a question you'll never have an answer to. And in fact, they say it's unscientific because we cannot imagine what's out there. But it turns out that's what destroys their theory, because if you cannot tell me what the white stuff is, you don't even have a physical interpretation. You cannot tell me what you're talking about. You have to identify the white stuff. You got to tell me what that white stuff is. Because if the balloon is expanding, why does a balloon stop there? What continues? That's what you got to answer. If you can't answer that, thought, I mean, you can say it's thought, if you cannot answer that question, you cannot even begin your presentation. You don't have a theory. Okay, a theory is what? An explanation. Okay, so they don't have an explanation for this balloon analogy. That ridiculous, really, because they think that the universe is this sphere and the galaxies are not really inside. What they are is on the outside, just on the surface of this expanding balloon. Okay, so all the galaxies are on the surface of the balloon. Like if you see a balloon that's polka dotted, and you blow the balloon, and all the little dots become bigger, but they also become separated from each other because the balloon is stretching, right? And so one of the questions that has always come up is, why don't the galaxies also get bigger and bigger and fly apart, kind of, as the balloon expands? And they say, well, locally, both gravitation and electromagnetism pull everything together. And then galaxies can separate from each other as the balloon expands. Okay, and then why does the Andromeda galaxy, why is it blue shifted? Why is it coming towards us and will apparently hit the Earth around 2.2 million light years in the future? 2.2 million years in the future because, it's, I guess, traveling at the speed of light. And so Andromeda is coming towards the Milky Way. And so is the rest of the local group. It's like they're all coming slowly together. And you're saying, well, hold it, the balloon is expanding and all these galaxies are on the surface. Should these galaxies have more distance between them as time goes by? That's not the case with the local group. The local group is coming together, and the answer to that is, well, here, gravity is stronger than dark energy. The dark energy is not powerful enough to overcome the attraction, the gravitational attraction between galaxies. That's the answer. Okay, so it's all ad hoc. Okay, they're trying to explain why when they look through the scope, they see what they see, and then they try to explain it, usually with equations, with mass, with gravity, and that's the science we have today, the mathematics that we have today. Okay, so there are some skeptics of dark matter, dark energy. I think, I don't want to put words in his mouth, but I think Mr. Toth, whom I talked about the other day, is an atheist or becoming an atheist or at least an agnostic in dark matter and dark energy. So dark energy could be just an artifact of the so-called cosmological constant. Einstein's cosmological constant, his biggest error, as he said, or the potential energy of a so-called scalar field, okay? Or maybe just energy of the quantum vacuum. Quantum vacuum. What is the quantum vacuum? All these particles that come in from the void, they make the void, and one comes in, well, both of them come in, they separate, and they live momentarily. It's called a virtual particle. Then they go back, forming part of the vacuum. And the question is, when they come out, do they leave a hole behind momentarily? Is there a hole in space? And what is that hole in space? If space is made out of particles, what's the hole? The hole in what? So this is the issue. They never were able to figure all these things out. Okay, they just talk about the particles coming out, doing this, and putting it back because they need that to explain what happens in the lab. That's their explanation. But then they don't take that extra step and say, well, when these two particles came out of being part of the vacuum, what was left behind? A hole in the vacuum, a hole in nothing. It's scary stuff, really. You wonder how much beer these people drink, Anyways, so he says, I believe that we need to find ways to, actually detect these dark thingies before we can say anything definite about their nature. Perhaps these dark thingies do not even exist. Ooh. Blasphemy. Blasphemy, because it's already been proven. And this gentleman, who is not officially a physicist, he says he's a part-time physicist, meaning that he's a self-taught physicist, mathemagician really, and he's suggesting something that goes counter to the catechism of the establishment, the party line, and that is that they've already proven that dark matter and dark energy exist, and he's questioning that. Okay, they are mirages of sorts because we are doing what? The math using the wrong theory of gravity. What he's working on is essentially a modified, called MOG, M-O-G. It's a modified gravity. That's what he's working at. He wants to modify the equation. He's saying out there at that distance, dark matter and dark energy do not really exist. What we have is simply a different equation should be used to mimic or describe what's happening at places like the edges of the galaxy or between galaxies. Okay, so they're looking at the equations. They're saying there is no real dark matter, dark energy. At least that's what they insinuate. Okay, that's their gut feeling, that there really isn't any dark matter, but they can't go out there and say it. because if they do, they're going to be, be ostracized. They're going to be kicked out of the club. And so they have to be careful what they say. And the worst thing they can say to a fellow like Toth is, "You're not a physicist, anyways. You don't understand." That's he died. They tell him that. Okay. Okay. Here we have another lady, Sabine Hassenfelder, and she says the low redshift supernovae were in one direction, while the high redshift ones were in another direction. Problem: it's a skewed sample. She was talking about these papers that analyze the fact that maybe, just maybe, um, dark energy doesn't exist. And again, she's in dark matter. Uh, just in case, also she has a little doubts. I think more than doubts on dark matter. Again, she's playing around with the equations. Okay, so all these people are playing with the equations, and they're not looking through the telescope, saying, "I'm not going to see this stuff, so why bother?" What I'm going to do is just do my calculations and try to mimic with the equation what these people are observing out there. And so it says a recent paper claims dark energy does not exist. Talk about blasphemy. She could get in trouble for this. If dark energy is real, the universe will expand faster and faster until all eternity. Okay? All this stuff pushing all the stars, everything outwards, right? If there's no dark energy, the expansion will slow down instead, and it might even reverse. In other words, dark matter triumphs over dark energy, so to speak. Okay? In which case, the universe will collapse back to a point. Okay, so apparently, this lady, she believes that we came out of a point, and we probably go back to a point known as the oscillating universe. We started out at a big bang, get to the big crunch, or maybe not even reach there. Somehow gravity pulls everything together again, and we go back to the point. And it's this point to expansion, back, point to expansion, back, and so on. So this is the oscillating universe. I guess she's thinking about, and she's trying to, describe that with an equation, that process, okay, of why matter comes back together to be a point. Okay, and here's the paper she's referring to. The fellow said the best fit to data rejecting isotropy and consistent with no acceleration. So he was saying there is no acceleration of galaxies outwards from each other. There is no dark energy essentially pushing all these galaxies outwards. Okay, thus the cosmic acceleration deduced from supernovae may be an artifact of our being non-Copernican observers rather than evidence for a dominant component of dark energy in the universe. So some people are starting to question, this came out 2019, by the way, so some people are starting to question, from the establishment, whether there is such a thing as dark energy out there. Is there something pushing all these galaxies outwards? Or was it simply from the initial Big Bang explosion, whatever that was, So we have this explosion, and it's like a hand grenade. You don't really need something pushing the little shrapnel, on and on and on. It's from the initial explosion that you got everything going outwards, so to speak, But even when you throw a hand grenade, the pieces don't come back together. But you say, well, there's not enough matter to produce this gravitational pull, okay? But that's what these people are looking at. They're saying, okay, there was this explosion, but now gravity is going to pull everything back together. And so that's what they work on. They work on the equations. They're simply trying to mimic with their equations, again, tautology, right? They're trying to make ad hoc equations that match what they observe out there. That's all that mathematical physics is. Do they have a mechanism? I mean, what is the mechanism? I'll concede dark matter. Let's start there. I'll concede dark matter. Bunch of particles, heavy particles, whatever. Okay, so you have all these loose, discrete particles all around the galaxy. What is the mechanism? By what mechanism do they compel stars to go faster? And by what mechanism do they prevent stars from leaving the galaxy? I mean, if they can't answer that, they don't have physics. What they have is just an equation that says this is the description. And that's where we stand today, okay? Okay, so here we have something we discussed the other day, and uh, I was supposed to put this as the question and answer segment, but it's part of this subject, so I'm just going to introduce it here in what I've been covering right now. And it's got to do with this. I showed this the other day that under the rope model, you have this linear regime, which is between any two stars. And on the right, we're going to have the sun, and on the left, we're going to have the Centauri system. And I'm saying that any object that tries to leave the solar system will encounter the bird's beak, which is a region that has no gravity. Okay, I call it the linear regime. Okay, and so here it is. You can see it again. You can see the sun on the right, the Alpha Centauri on the left. Okay, Proxima Centauri, whatever. And any rocket or whatever that tries to leave the solar system will encounter this region, this linear regime. Okay, that's at the end of the bird's beak. And this is how you would be traveling for eons through these ropes that come into each one of the atoms of your spaceship and you yourself. Okay. Why am I putting this up there? Well, I'll tell you why. Because a fellow asked the question. He says the following. He says, I don't quite get how the lack of gravity in the linear regime slows down the spaceship when in fact there's less fan out of ropes on it from either side. Yeah, I guess he has problems visualizing this. He's saying, look, the farther you get away from the sun, the fewer ropes you have, right? Because the ropes are coming together the farther you are. And he says, you know, we should be traveling, if anything, faster and not slower. Right now we have the pioneers, that's what this was all about. The pioneers are closer to the sun than they should have been. They should have been farther out. Okay, and so he's saying, how do you do it with ropes? I don't understand. Looks like that, the farther you go out there, the ropes come in and they become a single coaxial. You should be traveling faster rather than being pulled towards the sun. That's what he's questioning here, okay? My understanding of it is that considering the so-called mass weight of the spaceship relative to either star and the distance remains the same, the factor that might be changing is g, the gravitational constant g. The gravitation, oh, okay, there is the gravitational constant. It might not be a constant after all, okay? You should research that and do your calculations. I did quite a few of those on the gravitational constant. Now it's your turn. Okay. Is that what Bill is saying here when he states that Newtonian gravity is no longer at play here? Okay. And before I answer this gentleman, there's another gentleman who put a note. He says, so the ropes don't follow a straight path between objects? Why not? And I'm assuming, I don't want to put words in his mouth, but I'm assuming he's referring to the bird's beak. You can see there's a curve there. And so he thinks that the ropes there are curving. Okay? I think that's what he's referring to. He's saying, I thought they were all straight. They were all tight. And the answer is yes, they are all tight. And so let's answer this gentleman first. Okay? Then move on to the first one. Here it is. We can produce these patterns all with straight lines. And you can see they're curved. You say, how can it be curved? It's curved, but it's all done with straight lines. Okay, so all these two patterns were made with straight lines. And that's essentially what we're saying that happens in the bird's beak. We're doing it all with straight lines. In other words, we're doing it all with taut ropes connecting atom to atom. Okay, we're going to be producing a curve. Okay, a curve of the net, you can say, of ropes. We're going to produce a curve of the net through with straight lines. Okay, and so here, let me show you the bird's beak. Okay, this is the bird's beak, and I did this all with straight lines. Okay, all this is done with straight lines, but you can see a curvature at the top. And why is this curvature? Well, this curvature, we have to understand why, the cause, what triggers this. It's that if I ask you how many atoms are there at the top, at the pole of the sun, versus how many are in its equator in this picture. Well, you would say there are more atoms around the belly, the center of the sun, than they are at the very North Pole. In fact, at the very North Pole of the very South Pole, there should be a single atom that's out there, you know? And so there should be only a single rope from that atom to anything like to the Centauri system. On the other hand, if you look at all the atoms that are in the middle of the sun, there should be gazillions of them there. And so that's why you see more ropes running down the center, okay, what's going to become the linear regime, than you have at the top. Okay, so all ropes are connected from one sun to another, like from our sun to the Centauri system. So I put those ropes there, I drew those. But the reason you get that curvature is that as you go down this object, the sun, you should get more and more ropes as you get to the center of the sun. Okay, so that's what produces the bird's beak. And the bird's beak, as you can see, is not a perfect square of the distance function like is Newton's. Newton's would be a perfect triangle. In fact, I should have drawn that there. But Newton would be a perfect triangle. This is not a perfect triangle. This is a curved side triangle. Okay, it's not an exact triangle. Okay, so that's the situation there. Okay, so where do we go from here? Well, here you see the linear regime. Okay, and I've drawn the bird's beak on both our sun, which is the one on the guy on the right. I should have labeled that. And the one on the left is the Centauri system, Alpha Centauri or Beta, whichever, doesn't matter. So the issue is you can see the bird's beak there, okay? Why? Because again, most of the atoms are in the center of the sun and of the Alpha Centauri there, and relatively fewer, much fewer, are in the ones that go straight ahead from sun to sun, okay? So you should produce a bird's beak under the rope model, under the rope assumption. Okay. Okay, so here you have our starship, and it's going to leave the Earth. Okay, and so it travels, and when it's close to the sun, it's more or less square of the distance. So the rope model pretty much matches Newton, the point at A there. Okay, that's our rocket there at A, and the rope model essentially mimics or matches almost perfectly Newton's square of the distance function. No problem. But what happens when your spaceship hits the point where more and more the ropes go straight ahead from our sun directly to Alpha Centauri system? What you have is that linear regime. And there is no gravity because you don't have the square of the distance gravity in that region. And so what happens when your ship comes out of the sun, yeah, in this case out of the solar system, once it hits that region, let's assume it was just a fixed place. It's actually a gradient. Okay, it's a nuanced region, you could say. But let's assume that there's a clear-cut place. At that point where you hit the linear regime, well, what's going to happen, it's like if your rocket hit a brick wall, okay? And I liken it to a diver going from water to molasses, assuming it's that clear-cut. It's not, but this is just for illustration. If you go from water to molasses, you're going to be slowed down. And that's essentially what's happening. You can also look at the spaceship coming backwards from Alpha Centauri to the sun. You might expect, if you use the square of the distance, you might expect the rocket at sea, okay, assuming it's turned around facing the sun, it's going towards the sun, you might expect the rocket at sea saying, okay, I should expect, according to Newtonian square of the distance, I should expect being drawn to the sun here. And it turns out you're not drawn to the sun because it turns out that, you got to go further down if you want to have gravity. You're not yet in the square of the distance gravity regime. And so this is what's happening here. What's happening is that so what we're doing here is comparing Newton against the rope. In other words, how did these people calculate that the pioneers were not where they were supposed to? Well, they used Newtonian gravity. That's how they figured all this out. Okay, so let's understand the issue. The issue is that NASA, when they figured out that the pioneers were not as far out as they should be, they used Newton, and they used the square of the distance equation. But it turns out that the probes were closer to the sun. And the issue there is, again, it's like the rocket hit a brick wall, so to speak. It's nuanced. It's very gradual. In fact, that's what they measured, that it kept losing speed as it went along. Okay, so that's what you got to mimic with the equations. What they did was they went with the equations. They also said, oh, there was a heat dissipation there, and preferentially in the direction of travel, and that's what slowed it down. That was their argument. And I'm saying, no, what you have is this probe is moving into a region that is not quite Newtonian. Okay, it's not Newtonian. It's already changed, and there is no gravity in that linear region. So it's like if it hit a brick wall, it slows down. It's starting to slow down as it tries to move out of the solar system. And again, we're comparing the rope model versus the square of the distance model. Okay, so that's what we're doing. So don't think of it in terms of ropes. Are there more ropes, less ropes? What you got to compare is against Newton, because that's how they determine that they're slowing down or decelerating towards the sun. Okay, so that's the story. Essentially, the probes, Pioneer 10 and 11, they hit this region where there is no gravity. And so now instead of thinking in terms of Newtonian gravity, you got to think of a no gravity region, or fewer, actually it's less and less and less, but we're just going to talk about the extremes and say a no gravity region. And so now this thing is drifting, and you're expecting it to be farther out because of Newtonian calculations, and it's not there because it doesn't encounter gravity, or it encounters really less gravity as it goes, as it leaves the solar system. That's the story. Okay, anyways, we have a final issue. I'm going to address here, and fellow says, he says, you've completely intellectualized yourself out of the meaning of Christianity. Well, no, it's not true. I'm the Lord's messenger. I came here to educate, but we educate with, a baseball bat. I don't use a baseball bat because it's too big for the screen, so I use my dough roller. But I'm doing the Lord's work here on earth, okay? But if you expected me to, because of that, to, kiss and make up with all these people, no, we educate with a baseball bat here. Okay, with that, I'll see you next time. What is it, Sunday? We'll see you on Sunday. Bye-bye.